welcome to the next class. We will continue our discussions on the concentration cell. Earlier we had discussed about the electrodes of the first kind, second kind, third kind, etc. Now we are going to discuss about the concentration cell. So, in the previous in the previous cell discussions, we had put same electrodes, but solutions of different kinds, solution concentrations. Now, I am putting it in the form of this expression silver chloride, that is the electrode part, and it is dipped in a solution of chloride solution of unknown concentration x and chloride concentration of a known volume, that known concentration, that is standard, again connected with the silver chloride silver electrode. So, you can see that except the two except this part, that is chloride concentration, all other sides, all other parts of these left hand side and the right hand side are same. So, the only difference, if we can get any EMF, it has to come from the differences in the chloride concentrations. Now, let us this is how the arrangement goes, that is I have a chloride concentration here separated by a salt bridge, that means there is no direct contact with the ions except through the salt bridge, and then I have another electrode connected to a resistor and the power supply. So, this is the cell I am defining now. Now, suppose the standard is 0.1000 molar, it is a single electrode potential. I can write E is equal to E naught minus R T by NF ln oxidant by reductant. Instead of oxidant by reductant, I am going to write the numbers now. So, the silver chloride electrode E naught is equal to 0.222. So, because it involves only one single electron, I write 0.0591 by 1, that means 1 only. So, logarithm of this, and the reduced form is always 1 if it is metal. So, I delete that and then solve this, I get 0.281 volts. If the unknown is more concentrated, say 0.1500 molar, then the standard 0.100, then E x I can write half cell is equal to 0.222 minus 0.591 logarithm of 0.15, that works out to 0.271 volts. Now, what is the EMF you are going to see in this case? That is E standard minus E x, this is 0.281 minus 0.271 is 0.010 volt. Now, suppose the unknown is 0.680 instead of 0.1500. Instead of 0.1500, this is 0.680 molar. Then I can write a similar expression and I get 0.291 volts, and E cell what you actually measure is 0.010 volts. You will be surprised now which one to take the unknown concentration. That is, if the concentration is 0.1500, still you are going to observe only 0.10 volts. If the concentration of the unknown is 0.680 molar, still the difference what you are going to observe is 0.010 volts. So, any measured potential could correspond to two different concentrations, and different ambiguous interpretations are possible. So, you can avoid this ambiguous interpretation by noting that the interpretation corresponds to more positive of the two. So, the concentration cell provides a convenient tool for the analysis of pH if I replace the chloride solutions by hydrogen ion solutions. So, similar process should happen with respect to hydrogen ions. So, how do we define the pH? pH is defined as the negative logarithm of the activity of the hydrogen ion expressed in molarity, that is pH equal to negative log of AH plus, that is equal to negative log of H plus. Here we are going to neglect the activities because the solutions are very dilute and activity coefficients are expected to be 1. So, I am going to simply replace the activity terms by H plus. So, suppose you have a solution of 2 into 10 raised to minus 4 molar hydrochloric acid, then you can calculate the pH of this solution as negative log of 2 into 10 raised to minus 4, that is equal to 4 minus log of 2 and then 3.699, which is approximately equal to 3.7 volts. That means, given any concentration of the hydrogen ion concentration, you should be able to determine its pH. So, the measurement of pH is accomplished with the hydrogen electrode, as I had told you earlier, in a concentration cell. That means, I must have a standard hydrogen ion concentration and then an unknown concentration of hydrogen. So, the potential of such a system is given by E is equal to E cell. E cell should be equal to 0.0591 logarithm of the concentration of the standard divided by the concentration of the unknown. So, for a standard electrode, a standard hydrogen electrode, E cell is nothing but minus 0.0591 logarithm of H plus divided by oxidant divided by the reductant. Reductant activity is 0. So, it is log of 0 is 1. So, minus 0.591, negative log of H plus is pH. So, I am going to get 0.0591 pH, or pH is nothing but actual EMF divided by 0.0591, that is the RT by NF value. So, if I use a calomel electrode instead of a standard hydrogen electrode, I must be write E cell minus that of the calomel electrode, that is 0.246 divided by 0.50591 volts. Why do I go for a calomel electrode? That is because standard hydrogen electrode is difficult to set up. So, calomel electrode is very simple. So, if I use a calomel electrode, it gives reproducible values and I can measure the pH very simply just by connecting this thing. Still better option would be to use a glass electrode. So, what is a glass electrode? A glass electrode is a thin membrane of a certain variety of a very thin membrane of a in the form of a bulb, in which I am going to put some solution and seal it at the top with a wire in between, and then I put another solution outside the glass bulb. That means, the glass membrane is in contact with a solution of standard solution, which is sealed inside the membrane, and another solution which is outside the membrane. Therefore, it is essentially a concentration cell. So, I can represent the concentration cell like this, that is inner SCE, that is look at this slide please, and this inner calomel electrode. The electrode, instead of standard, I put pH 7 buffer, then I have a glass membrane, then I have a test solution which is connected again to external SCE. The EMF corresponding to this and this will get cancelled because one is positive, another is negative. So, the only difference in EMF should come from the test solution and pH 7 buffer, that is a standard concentration. So, this is how a glass electrode will look like. I have a silver chloride electrode with a connection outside. This is a glass tube and it is a small bulb here, and then in the bulb I have silver chloride electrode, that is this one, and then I have a solution chloride containing buffer. So, this if I dip in a solution of unknown concentration, it sets up a concentration cell. So, for such a cell, pH is given by Eg, that is asymmetry of the EMF of the glass cell minus E cell divided by 0.059 volts. Eg is a constant that includes the potential of reference electrodes and some additional small spurious potentials called as asymmetry potential. It arises out of unequal strain in the glass, because every glass membrane is unique. Therefore, the strains or asymmetry potential would be different for each glass. Therefore, it is included in as a constant in this equation. So, the glass electrode is a routine analytical tool in any laboratory. In highly alkaline solutions, you may not get very good results, very correct results of pH, especially above pH 10, and the error may be as high as 1 pH. The glass surface can also absorb some specific ions which may cause erroneous results. That is, apart from hydrogen, it may absorb some other ions also. And a great branch of electrochemistry has been electrosensor technology has been built up around this property of the membranes capable of exchanging the ions, and these are known as specific ion electrodes. So, apart just like hydrogen ions, you can construct a glass electrode or an electrode which is responsive to fluoride ions, ammonia, cyanide, and then carbon monoxide, carbon dioxide, like that several systems you can design by providing a ion specific membrane, and such electrodes are known as ion selective electrodes. We are not going into details of the ion selective electrodes as such, but this is the point where the theory of ion selective electrode starts. So, the glass surface, since it can absorb specific ions, it is a very good way of controlling the concentrations. Therefore, it is essential to rinse, because once you have a solution and then you dip your glass electrode in that, it is already set up an equilibrium and you want to measure the pH of another solution. Now, the glass surface is having the concentration of the previous ions, that is memory. So, you have to keep on washing it number of times until all the memory effect goes away, and then you are going to introduce your solution into that. That is why we always say wash a glass electrode with copious amounts of water before you proceed with the measurements. That is a good laboratory practice. Now, these are some of the ion selective electrodes what I was talking about. This is a silver chloride electrode and this is a porous glass membrane, this is liquid ion exchanger. And similarly, I can have silver nitrate solution, and if I have a silver halide membrane here and which is permeable to halide, then I can determine chloride ions. nitrate ions, like that. Different, this part which is the membrane or a crystal is going to play a very important role. And then I can have a silicon rubber membrane impregnated with silver halide. Different constructions of the electrode, ion specific electrodes, and several ion selective electrodes are marketed routinely in the for the analytical determination of the specific substances in water or soil or air or any other matrix. Specific ion selective electrodes are being marketed by several reputed companies. Now, let us look at QUINHYDRONE electrode. It is nothing but a variant of the glass electrode which can be used to measure the pH. Now, in QUINHYDRONE electrode I have a platinum wire and it contains QUINHYDRONE, that is 1,4 keto groups at 1,4 position, benzoquinone and quinine, and then in presence of hydrogen ions it can get reduced to OH. So, the EMF is given by E naught plus 0.0591 logarithm of H plus. Again I am going to neglect the reduced species, and then this is E naught is 0.699, and then 2 hydrogen, 2 electrons are there. So, I have to take twice, and this is another similar electrode with glass, like glass electrode, but it is not useful for pHs above 9, and in presence of strong oxidizing and reducing agents it will not work, because the hydroxy groups can get converted to ketonic groups in presence of oxidizing agents, and ketone groups can get reduced to hydroxyl groups in presence of strong reducing agents. So, it has got somewhat limited applications, but we do have a metal wire like antimony. You can take antimony electrode, coat it with antimony oxide, and then make an electrode out of that, and the reaction is given by 2 antimony plus 3 H2O going to Sb2O3 plus 6 H plus 6 E minus. This electrode is not as fragile as a glass electrode, nor it would show variations of pH depending upon the presence of oxidizing and reducing species. So, the potential of this electrode depends on the method of preparation and on the nature of the solution, but I can use such an electrode, in process solutions where the process solutions are moving at a very fast velocity. That means, if I insert a glass electrode in a fast moving solution, it may not be able to show the correct pH, or it may get broken or something like that can happen. But if I have an antimony oxide electrode, then I can measure the pH under harsher conditions. That is the idea. So, a great many reactions may be followed by potentiometric titrations, provided there is addition or removal of some ions for which an electrode is available. Thus, acid base titrations, hydrogen ions are being removed or OH ions are being removed, hydrogen ions are being added. So, one ion is being removed, another ion is being added. If one of them is responsive to EMF changes, that is potential changes, the reaction can be followed by potentiometry. So, we can have different kinds of reactions like acid base reactions, precipitation reactions, redox reactions, complexation reactions, etc. All these things can be followed by potentiometry. Only thing is, what you need is a pH electrode or a reference electrode, specific electrode and a reference electrode. Reference electrode could be a pH electrode, glass electrode or a calomel electrode, one of the two would be fine. And then the potential can be measured and you can plot the pH versus the amount of the titrant added, or you can plot the potential also. So, if you take a look at this figure, at this slide, the pH is given by E cell minus 0.246, that is the reference electrode potential, divided by 0.0591, and if the curve is essentially vertical in its steepest portion, equivalence point is easily reached. Otherwise, derivative plotting is more useful. Let us consider the titration of 100 ml of 0.01 normal HCl with 1 normal NaOH. That means, the NaOH is already 10 times 100 times more concentrated than the titrant. This is 0.01, this is 1. So, that we can calculate the values of the potential and pH. This is a very simple calculation and I have put it in the table. So, when you have not added anything, the hydrogen ion concentration is same as 0.01 normal, that is, it is a strong acid, 100% ionized. So, the H plus is 10 raised to minus 2 and pH is 2 and potential is 0.364. Suppose you add 0.5 ml, the following the 50% of this would be reduced, would have reacted and the concentration would have come down by half. So, 5 into 10 raised to minus 3, the pH would change to 2.3 and 0.372. Similarly, 0.9 you get pH 3 and 4.423 you will get, and then 0.99 if you go, pH would be 4 and 472. You can work out these numbers yourself and satisfy that the pH changes and EMF changes are accurate. Now, when I add 1 ml of this, because it is 100 times more concentrated, there is complete neutralization and we know that at under neutralization conditions pH is 7. So, I have a pH 7 here and the EMF is given by 0.659. Now, I add 0.0001 mole, 1 volume, a milliliter of the NaOH excess. Now, what happens? The pH will become 8 and the EMF will become 0.718. And similarly, if I add 0.001, I will have pH 9, 0.777 and then 1.1 ml, 0.1 ml extra. If I add, I will have 0.895 and 2 ml I will have 0.954. So, if I plot EMF versus the concentration, I would end up with a figure like this, what is there on the left side. So, a very sharp peak you will get with a sharp inflection point. So, similarly, I can go for other systems. These are the potentiometric curves, what you would see with the titration of NaOH and HCl on the left side, very sharp inflection point. You will see that the within a fraction of a milliliter you are going to end up from one end to the other end. That means, you will get a very beautiful end point somewhere in the middle here. And if you plot pH, you would see that changes from 3 to 9 or 10 would be visible with again a very sharp end point. See, the midpoint of this vertical portion is the end point of the reaction. Now, these are some of the potential curves, potentiometric curves. This the top one is 0.1 normal aqueous ammonia titrated with HCl. Here you can see the sharp point is, one point is here and another point is somewhere here, the inflection point. So, I can have an indicator which can change color in this region as well as in this region. So, if I have only one end point, strong acid and strong base, I will have a very sharp end point, single this thing. With dibasic, I will get two inflection points. Tribasic, I get 3 inflection points. Like that, you can see different kinds of potentiometric curves in this. For example, this is sodium bicarbonate titrated with the acid. Here you will see that the inflection point is not so well defined, but still you can see it, because this is the area where the inflection point, and phenolphthalein or thymol blue will change color in this range to this range. That means, inflection point is covered. So, you can, there is another inflection point somewhere here, that is corresponding to pH 3 or so, and then there is another indicator. So, we can carry out the reactions like this without involving much problem. So, what are we saying is acid base titrations can be followed by measuring the EMF, and you can get accurate endpoint. Now, is it possible only for acid base? The answer is no. The titrations involving precipitations are also conducted using potentiometry. What is the need for conducting potentiometric titrations for precipitation reactions? Because the end point is not easily detectable, especially in presence of precipitate. So, you may overshoot the end point at any time. So, you will not be able to stop the reaction at the exact point. In such a case, you should go for potentiometric titrations, and then involving precipitation. But such titrations can be performed very easily. Consider the reaction of silver ion with chloride ion. Now, we are going to consider 0.01 normal silver nitrate against 1 normal sodium chloride. That is, again there is a 100% difference in the concentrations of the titrant and the titrand. So, the potentials can be calculated by using the Nernst equation. E cell is equal to 0.553 minus 0.059 PAG. I am writing this because it is the negative log of Ag silver concentrations I am going to write. At the equivalence point, what happens is silver ion and chloride ion are equal, and the product of this works out to 1 into 10 raised to minus 10. That means, the silver ion concentration should be square root of this. So, if I take the square root, I can calculate that the silver ion concentration in a precipitation reaction would be 10 raised to minus 5 molar at the equivalence point. Now, take the titration. Look at this, I have made a similar table like acid base titration. I have put Ag plus and PAG, that is negative log of Ag plus, and E, and then I have put 0.00, 0.9, 0.999, 1.00, 1.1 and 2 etc., and 0.435, 417, you are going to get 0.376, 0.317 and 0.270. At 0 exactly equivalence point you will get 0.258. After that the decrease starts and you will end up with 0.081. Now, what happens if you plot these things? You will see a beautiful curve here. Similarly, for other halides, this is the titration for silver nitrate. The curve will be similar to acid base titrations, and the precision obtainable depends upon the degree of insolubility of the precipitate. If the precipitate is highly insoluble, the precision would be very good. If the precision solubility is more, or if the substance behaves amphoterically, the endpoint will not be sharp. So, if the product is somewhat soluble, the slope of the curve at the equivalence point would be less steep and more difficult to assess also. So, reactions involving complexations exhibit more complicated titration curves. In the titration of silver against silver cyanide, if we consider, you will see that we have a reaction going like this: silver forming a cyanide AgCN precipitate, followed by again it dissolves forming AgCN2 minus. That means, if you start the reaction, take the cyanide and add silver plus, more of cyanide is at the bottom, less of silver is there. First it will form AgCN2 minus. So, there it will be dissolving, and then as you increase the addition of silver, all the AgCN2 minus would be formed, but then the cyanide it will form a precipitate. So, AgCN will be forming. So, near the start of the titration we have AgCN2 minus. At the completion of this reaction, the potential of silver shows a sudden decrease, after which the insoluble silver cyanide will start precipitating. When all the cyanide is used up, another jump in the potential will occur. Other examples of such precipitation titrations involve the substances whose solubility products are very low, that is iodide, then bromide, then chloride and thiocyanate, etc. Is it possible to determine all the mixtures of chloride, cyanide, bromide and iodide, etc.? The answer is yes, and the first equivalence point will correspond to silver cyanide, and second one will correspond to the next highly insoluble precipitate. Among the halides, iodide is having lowest KSP. So, the next one will correspond to iodide. Next inflection point in the curve would correspond to iodide, next one would be to bromide, next one would be to cyanide, chloride, etc. So, it is possible for us to determine the various endpoints like this. On the right hand side, I am showing you first inflection point will correspond to cyanide, and then iodide, then bromide, then chloride, etc. So, all these reactions are easily followed by potentiometric titrations. Now, we can look at oxidation reduction reaction titrations. These are followed by a simple platinum indicator electrode and saturated calomel electrode. One reference you will need anyway, that is reference electrode. It can be SC or silver chloride electrode or any of the known electrodes. And when we consider the reaction of stannous chloride with sulphate, ceric sulphate, the reaction we can write it as SN2 plus ceric going to SN4 plus, that is stannic, and 2 moles of cerous. And the equilibrium constant of this reaction is given by the products divided by the reactants, that is SN4 plus I am writing here, C3 plus whole square I am writing here, and divided by SN2 plus and ceric 4 plus ceric. At the start the ratio of stannic to stannous is nearly 0. That means, before I add any ceric, the most of it would be in the stannous. That means, the stannic to stannous would be 0 and log of SN4 plus divided by SN2 plus, that is stannic to stannous log value would have a large negative value, because the concentration of the denominator is almost near 0. So, it will have a very large negative value. Now, after the first addition of the oxide, some of the stannic gets converted to stannous. The moment we have stannic and stannous, we can write Nernst equation, that is E is equal to E naught stannic by stannous plus 0.0591 divided by 2, that is RT by NF value divided by 2, because N is 2 here, and logarithm of the oxidant divided by the reductant. Remember that both the oxidant and reductant are in solutions now. So, they will have a definite concentration. So, some ceric is also present now. So, we can write another equation, Nernst equation for ceric cerous system, that is E is equal to E naught ceric cerous plus 0.0591, only single electron is required, and ceric to cerous plus ceric to cerous. But the EMF, if you are using only one electrode and one reference and one standard, the EMF value cannot be two different values for ceric and cerous and stannic and stannous, because all the 4 species are in the same solution. It has to show only one EMF value. Therefore, we can compare these equations, and reorganize. How we are going to do that is like this: put all E naughts on one side and solution terms, concentration terms on the other side. So, E naught C 4 plus by C 3 plus E naught SN 4 plus by SN 2 plus should be equal to this 0.0591 by 2 logarithm of stannic to stannous minus twice logarithm of ceric to cerous. Now, this is I can simplify this. See, 2 will become square here. I take out the log and then SN 4 plus into ceric 3 plus whole square divided by SN 2 plus and ceric 4 plus. So, this value is nothing but the equilibrium potential, equilibrium of the value of the reaction. So, I simply write log k. So, instead of writing all this, I simply put it as 0.0591 by 2 logarithm of k. Now, substituting the known values of the E naughts for stannic to stannous and ceric to cerous, we get 1.61 minus 0.15 divided by 0.0. These values are obtainable from the standard reference table I had shown in the last class, ceric to cerous, stannic to stannous, etc. And log k, this value should be equal to, or k should be equal to 2.5 into 10 raised to 49. So, at the equivalence point, the concentration of steric should be twice that of steric should be half that of stannic. That means, twice stannic is equal to steric and twice stannous would be equal to serous, and we can write this stannic to stannous and steric to serous, this is twice, so 2 plus 1 is 3. So, the cube root of this corresponds to the concentration ratios of the stannic to stannous and steric to serous. So, the species you can concentrations you can easily calculate at the equivalence point. Now, we can now substitute that value, that is what did we calculate in the last this thing 2.92 into 10 raised to 16. Now, we are going to substitute these values 0.15 into 0.0591 logarithm of 2.92 into 10 raised to 6, that becomes 0.64 volts. If I substitute calculate with respect to other electrode, that is other species, then also I should get the same value, but it has to be with a negative value. So, 1.61 minus 0.0591 logarithm of 2.92 into 10 raised to 6 should be equal to 0.64 volts. That means, we get this exactly the same value. That means, our results are accurate. So, note that the same value is obtained both ways, this is expected anyway. So, many redox reactions, especially those of permanganate, dichromate, nitrate and other similar oxidants have a strong dependence on pH. So, you can recall that the steric to serous reaction is nowhere we have written the pH or acid value. That means, it is independent of the pH, but several redox reactions are pH dependent. Some of them will proceed in the right direction in presence of acids, some of them will proceed only in presence of alkalis. So, pH dependence also we have to factor in if we want to talk about the complex reactions. So, that is redox reactions. The potential calculations also will become subsequently complicated. One such example is reduction of potassium permanganate, reduction of permanganate ion by iron. So, if you take iron ferric and add potassium permanganate, the ferrous will become ferric and permanganate ion will become manganese ions. So, we can write the equations like this, that is MnO4 minus plus 8H plus 5E going to Mn2 plus 4 plus 4H2O. This is for the manganese, and 5Fe2 plus going to 5Fe3 plus 5 electron. You add up both and these 5 electrons will get cancelled. You will have a reaction of MnO4 minus plus 8H plus 5Fe2 plus going to 5Fe3 plus Mn2 plus 4H2O. These electrons will get cancelled. Now, for this you can write an expression like this: E is equal to E naught plus 0.059 divided by 5, because 5 electron system, a logarithm of the products divided by the reductants. So, for manganese I have to write like this, and if I insert the value of E naught, I will end up with such an expression. Now, we have a similar expression for ferric to ferrous. So, the reaction is 5 electron system now. So, E is equal to E naught of 0.059 divided by 5 logarithm of ferric to ferrous. So, I can write like this, and at the equilibrium both the manganese side, Mn side and ferric side, iron side can be equated, and logarithm of by exchanging the terms on the left and right and rearranging, I get logarithm of manganese 2 plus Fe3 plus raised to 5 divided by MnO4 minus multiplied by Fe2 plus and H plus raised to 8 equal to 63.5, or K would be equal to 3 into 10 raised to 63. The large value of K in this case shows that the reaction is virtually complete. That means, you take iron, you take ferric, add permanganate, take ferrous, add permanganate, it will immediately go to ferric and manganese will get reduced. That means, very fast reaction, because you can simply, by knowing the value of K is equal to 3 into 10 raised to 63, you can simply predict that the whole reaction would be instantaneous. So, suppose we take this further for titration. Now, if I do that, I can titrate 10 ml of 0.1 molar potassium permanganate with 0.1 normal ferrous sulphate, and at the equivalence point ferric concentration I will know and manganese concentration I will know. So, at the equivalence point ferric would be 0.01 normal and manganese would be 1/5 of this, that is 0.002 normal, 1/5 of this concentration, and Fe2 plus is unknown, because at that time most of the ferrous would have got converted to ferric, and how much of ferrous is there we do not know. So, a little excess of permanganate solution at the equivalent point, if I add, how will you add? A little excess means 1 drop basically. So, if you add 1 drop, that approximately corresponds to 0.02 normal, 0.02 milliliter. So, if I add 1 drop of the permanganate excess, that is 0.05 milliliter, then I can write this expression 0.05 multiplied by 0.1 divided by 100, that is the volume I am taking. So, the concentration would be of the permanganate would be 5 into 10 raised to minus 5. You just solve this, you will get this number. So, substituting these values in the equilibrium equation. Now, let us substitute K is equal to, if you go back, Mn2 plus Fe3 plus MnO4, all these things I am going to substitute now. 2 into 10 raised to minus 3, 1 into 10 raised to minus 2 divided by these values, and what I get is x is equal to 5 into 10 raised to minus 15. So, the concentration of ferrous at the equivalence point, without actually measuring, just by continuing the reaction, I can calculate it to be 10 raised to minus 15 molar. That is a beautiful thing, a wonderful way of determining the concentration of a substance which you cannot see. And potentiometric titration permits us to do this kind of tricks. So, let us consider another redox reaction, that is ceric to cerous. Corresponding reaction would be ferrous to ferric. That means, if I take ferrous, add ceric ion, ferrous will get converted to ferric and ceric ion would get converted to cerous. This slide shows the actual reaction. steric 4 plus Fe2 plus going to steric 3 plus Fe3 plus. So, we can write the expression Nernst equation E1 is equal to E1 naught, and this I can replace it with a known value, that is 0.75 plus 0.0591 1 electron system. I do not bother log of Fe3 plus by Fe2. I have to write both these equations because both the solutions are, both the chemical species are in the form of solutions. Now, similar reaction I can write 1.45, that is for steric serous, that is E naught value, and steric serous I can write here. Again you would remember that both the species are in solution. So, at the equilibrium the rate constant is given by, I can put this value and this value, this expression and the next expression I can equate, and I can calculate the value of K is equal to log of steric serous into ferric divided by steric and ferrous, that is products divided by reactants, is given by 1.45 minus 0.75, that is the E naught differences, divided by 0.591 volts, that corresponds to 11.84, or K should be 7 into 10 raised to 11. Negative log of this would be 7 into 10 raised to 11. Again the value of the electrode potential shows us that the reaction is very complete, otherwise you will not end up with values like 7 into 10 raised to 11. You would always it is a fantastic feeling, because if it is 10 raised to 1 or 10 raised to 2, 10 raised to 2.5 like that, then it may not be a virtually complete reaction, but 10 raised to 11 means it is a virtually it is a complete reaction. Now, up to the equivalence point, all the steric ions will be utilized to oxidize ferrous to ferric. So, we can write the steric ferrous to ferric equations like this: when 10 ml of steric sulphate is added, 10% is oxidized, 90% is still in the reduced phase. So, oxidized species divided by reduced species, if I put the value of 0.75, I will get 0.69 volts. Now, 50 ml when I add, 50% gets oxidized and 50% remains unoxidized, and this is 0.75. So, 90 ml if I add 90 by 10, 99 by 10 similarly, and then 99.9 divided by 0.01 volts, that is 0.69 volts. You have to remember here that the values are changing almost in an arithmetic fashion, that is 69, 75, that is 0.06 difference, and then 75 to 81 is again 0.6, and 81 to 87 is 0.6, and 87 to near the end point is a big jump here. And you have to also remember that we are neglecting the dilution effects, otherwise it should be 10 by 110, but we are neglecting the dilution effects, because that is why we are taking the concentrations. Concentration of one to other is at least 10 to 100 times. So, that we do not have, we can neglect the dilution effects. So, when I have 100 ml added to that, the EMF would be average of the two, that is E1 plus E2 by 2, because the concentration terms are going to cancel out, because all the reactants have reacted with all the reactants have reacted and the products are formed. So, the EMF would be corresponding to the only the E naught values, that is E1 by E2 by 2, that corresponds to 1.10 volts. Now, when I add steric extra 0.1 ml, I will have 1.27 volts, and 101 ml I will have 1.33, again 0.6 volts difference, and 1.39 again 0.6, again 0.6 volts. Now, on the right side again it is assuming a very standard format, except at the equivalence point from 1.27 to 1.10, there is an error there, it should be 1.10, 1.1, and previous one would be 0.69. From 69 it jumps to 1.1 and then it jumps to 1.27, a big jump. So, at 99.9 ml I can calculate the PFE, that is just like pH I can calculate the PFE. Ferrous concentration would be 0.1 into multiplied by 0.1 divided by the total volume of the solution, that is 199.9, that will be 4.3. At 100 ml it will be 5 into 10 raised to minus 2 divided by 8.5 into 10 raised to 5, that would be 6 into 10 raised to minus 8, or P would be, PFE would be 7.2. At 100.1 Fe3 plus remains practically unchanged at 5 into 10 raised to minus 2 normal, and if I put this value Fe2 plus can be calculated to be 10. Now, PFE change, look at the change of the PFE values, 0.1 ml difference before the equivalence point it is 4.3, at exactly 100 it is 7.2, 0.1 excess it is 10. So, 4.3 to 7.2 to 10 within a volume change of 0.00, the 99.9 to 1, that is 0.3 ml, 91 and 2, between 0.2 ml the PFE changes from 4.3 to 10. So, these values are important for the choice of indicators. These values also indicate that the reaction can be very easily followed. So, how we follow the reactions, such reaction, all redox reactions, complexation reactions, etc., we will discuss in the next class, that is with a potentiometer.